It didn't arrive loudly. It didn't announce itself. It simply appeared, already moving faster than expected. When astronomers first detected ThreeI Atlas, initial calculations placed it among the growing catalog of interstellar visitors. Another object passing through, another fragment from elsewhere, another opportunity to test models already strained by distance and noise. At first, nothing seemed out of place. The object's initial velocity exceeded solar escape, as expected for an interstellar arrival. Its brightness fell within projected bounds. Its early orbital solutions converged quickly enough to suggest routine classification. Then, within days, something changed. The numbers stopped behaving. Trajectory updates began to diverge instead of tightening. Velocity estimates increased rather than stabilizing. Minor corrections, normally buried deep inside uncertainty margins, started accumulating into a pattern that refused to smooth out. ThreeI Atlas was not just moving through the solar system, it was behaving in a way that resisted early closure. Not dramatically, not in a way that triggered alerts or press releases, but in a way that quietly forced recalculation. As additional datasets were folded in, analysts noticed that the object's velocity curve refused to settle. Under classical dynamics, uncertainty should shrink as observations accumulate. Noise gives way to clarity. Error bars contract. With ThreeI Atlas, something asymmetric occurred. Uncertainty tightened in some parameters while expanding in others. That asymmetry mattered. The object was not simply fast, it appeared to be getting faster relative to expectation. This distinction is subtle, but it is critical. Interstellar objects arrive with excess velocity. That alone is unremarkable. What drew attention here was not speed itself, but the persistence of deviation across successive orbital solutions. Each refinement should have reduced ambiguity. Instead, ambiguity reorganized. The acceleration was small, measured in fractions, buried inside margins of error large enough to dismiss. Yet it kept appearing, again and again. When analysts attempted to attribute the behavior to solar radiation pressure, the numbers strained. Photons can push, radiation can impart momentum. This mechanism has been invoked before, particularly for low-mass bodies with high area-to-mass ratios. But for an object of ThreeI Atlas's inferred size and density, the effect should have been negligible. The equations closed, but barely. The solution worked only under narrow assumptions, requiring surface properties that were technically possible but statistically rare. The math balanced. The behavior did not relax. That explanation should have resolved the anomaly. It didn't. Outgassing was the next refuge. It always is. Jets of sublimating material can impart thrust. They can accelerate a body without engines, without intent, without mystery. This explanation has absorbed countless irregularities across decades of cometary observation. But here, the expected signatures failed to fully materialize. No broad coma enveloped the object. No chaotic plume expanded outward. No turbulent tail flickered with instability. Instead, observations hinted at something more constrained. Directional consistency. Whatever force was acting on ThreeI Atlas did not wander. It did not pulse erratically. It did not fluctuate with thermal cycles in the way volatile release often does. It appeared to persist along a limited axis, as though regulated rather than released. This did not break physics, but it leaned on the edge of it. At this stage, Avi Loeb's commentary began circulating, not as a declaration, but as a reframing. Loeb did not argue for an exotic conclusion. He did something more unsettling. He questioned the speed with which ordinary explanations were being accepted. Loeb did not assert what ThreeI Atlas was. He emphasized what the data allowed and what it resisted. Non-gravitational acceleration without obvious mass loss had precedent, he noted. But each precedent relied on invoking uncommon material properties or finely tuned conditions. Possible, but not typical. That distinction mattered. As more observatories contributed measurements, attention shifted away from speed alone and toward orientation. Objects traveling through interstellar space for millions of years are expected to tumble chaotically. Small perturbations accumulate, axes drift, rotational states destabilize. ThreeI Atlas did not follow that script. Its rotational behavior appeared unexpectedly stable. Stability simplifies motion. Stability preserves direction. Stability allows small forces to compound. This realization quietly reframed earlier assumptions. If ThreeI Atlas maintained a consistent orientation, even a modest non-gravitational force could accumulate measurably over time. Acceleration no longer needed to be dramatic. It only needed to be persistent. Mass estimates deepened the unease. ThreeI Atlast appeared larger and denser than previous interstellar visitors. A heavier object, maintaining coherence while resisting deceleration, narrowed the range of comfortable explanations. Energy was involved. Not explosive energy, not transient energy, sustained energy. This did not imply propulsion. It did not imply guidance. But it did imply a mechanism not yet observed in passive bodies under similar conditions. As the object continued inward, its geometry relative to the solar system became harder to ignore. The trajectory carried it unusually close to the plane in which the planets orbit. This alignment increased detection probability and gravitational interaction. Interstellar space does not privilege the ecliptic. Random arrivals should scatter across angles. ThreeI Atlas did not. Probability alone does not assign meaning. Astronomy routinely encounters low-likelihood events simply because the universe is vast. But probability establishes pressure when paired with behavior. Acceleration that persists, orientation that remained stable. Geometry that favored interaction. Each element, in isolation, remained explainable. Together, they no longer felt independent. By the time ThreeI Atlas entered regions where gravitational influences grow complex, the conversation shifted again. The object was approaching a zone where small perturbations can produce disproportionate outcomes. Jupiter lay ahead, not as a destination, but as a test. Near Jupiter's sphere of influence, trajectories become sensitive. Natural bodies pass through such regions routinely, their paths altered by gravity alone. Yet ThreeI Atlas arrived with a combination that was increasingly rare: speed, stability, timing. Minor changes here could redirect the object significantly. Whether those changes would occur naturally remained unknown. No evidence suggested intervention. No evidence suggested avoidance. But the openness of the future path mattered. At this point, the investigation did not escalate into alarm. It narrowed into focus. Scientists recognized that the next phase would be defined less by explanation and more by observation under constraint. Windows close quickly in orbital mechanics. Missed data cannot be recovered. ThreeI Atlas did not announce danger. It did not broadcast intention. It did something quieter and in some ways more unsettling. It forced models to stretch without breaking. As calculations continued and predictions updated, one fact remained unchanged. The acceleration, however subtle, did not vanish. It lingered, quiet, persistent, unresolved. And in celestial dynamics, unresolved persistence is often where ordinary categories begin to thin. The unresolved persistence of motion changed how ThreeI Atlas was discussed. Up to this point, uncertainty could still be framed as noise. Measurement errors shrink with time. Anomalies soften as models improve. Most unusual detections end this way, not with revelation, but with normalization. Patterns dissolve into averages. Deviations fade into margins. ThreeI Atlas resisted that process. As weeks passed, orbital refinements did not converge toward a single calming explanation. Instead, they began clustering around a shared discomfort. Independent teams, working with different telescopes, different reduction pipelines, and different assumptions, arrived at results that refused to cancel one another out. The deviation was real, not large enough to declare, not small enough to ignore. Each update narrowed uncertainty while preserving the anomaly. This was the opposite of what analysts expect. In celestial mechanics, convergence is reassurance. Divergence invites scrutiny. Persistence, however subtle, becomes evidence. At this stage, attention returned to non-gravitational forces, but with far less tolerance for hand-waving. Outgassing was revisited, this time with detailed thermophysical modeling rather than broad analogies. If sublimation were responsible, the distribution of volatiles would need to meet unusually strict conditions. Surface ice would have to release material directionally. The release would have to remain stable over extended periods. And the mass loss would need to be efficient without producing a visible coma. This combination is not impossible. It is simply rare. Observationally, the object did not behave like an actively eroding comet. Its brightness profile lacked the diffuse halo typical of volatile-rich bodies. Instead, luminosity remained compact and contained, suggesting that any material leaving the surface was doing so in a constrained manner. Control does not imply design, but it does imply structure. That distinction mattered more than it first appeared. Spectral analysis complicated the picture further. As solar exposure increased, the expected dominance of water signatures remained muted. Carbon-based compounds appeared more prominent than models predicted for an object undergoing progressive heating. The balance was not wrong, but it was unexpected. This imbalance shifted interpretation away from standard comet analogs. ThreeI Atlas did not resemble a fresh, icy fragment shedding layers under thermal stress. It appeared comparatively resilient. Resilience under stress is not accidental. It emerges from configuration. As the sun's influence intensified, rotational dynamics came back into focus. Objects subjected to uneven heating typically respond with torque. Spin states drift, axes wander. Minor imperfections amplify into instability. ThreeI Atlas did not display that behavior. Measurements before and after key orbital milestones suggested that its rotational orientation remained largely intact. Any wobble that existed stayed bounded. The axis did not precess freely. It did not tumble chaotically. This stability had consequences. A stable orientation allows forces, however small, to act consistently. Over time, consistency outperforms magnitude. What cannot be achieved explosively can be achieved incrementally. Acceleration did not need to spike, it only needed to accumulate. At this point, Avi Loeb's analysis gained traction, not because it proposed an answer, but because it articulated the discomfort clearly. Loeb did not argue against the data. He argued that the data was being explained too quickly. The object's behavior occupied a narrow regime where conventional explanations remained technically possible, yet increasingly strained. Each explanation worked, but only in isolation. Each required assumptions that did not comfortably coexist with the others. This distinction mattered. Science does not advance by declaring impossibility. It advances by identifying tension between expectation and observation. ThreeI Atlas sat squarely within that tension. The trajectory geometry deepened the unease. The object's path through the solar system was not arbitrary. Its inclination relative to the planetary plane was modest, placing it close to the region where observational coverage is densest and gravitational interactions are most complex. This alignment increases detection probability, introducing bias. But bias explains visibility, not behavior. ThreeI Atlas did not merely appear aligned, it was aligned. For an interstellar object arriving from random stellar traffic, such alignment is statistically disfavored. Not prohibited, simply unlikely. Low probability events occur. They occur more often than intuition expects. But probability becomes meaningful when paired with consequence. An object traveling near the planetary plane experiences stronger gravitational coupling. Encounters become more frequent. Perturbations become more efficient. Small forces matter more here than they do in the outskirts. ThreeI Atlast entered a corridor of influence rather than skirting the edges. As its future path was projected forward, one encounter stood out. In the coming years, the object would pass near Jupiter's sphere of gravitational dominance. This region, defined by the planet's Hill radius, marks a threshold where minor changes can lead to disproportionate outcomes. Natural bodies pass near Jupiter routinely. Most are scattered. Some are redirected. A few are temporarily captured. Gravity alone accounts for nearly all of these cases. What mattered here was not the encounter itself, but the conditions under which it would occur. ThreeI Atlast would arrive with excess velocity, with a stable orientation, with unresolved non-gravitational acceleration. In such a regime, prediction becomes fragile. No model suggested intent. No data indicated maneuvering. But the sensitivity of the system meant that forces already under scrutiny, forces considered marginal elsewhere, could influence outcomes disproportionately here. This should have simplified interpretation. It didn't. At this stage, the investigation entered a new phase. The focus shifted from classification to consequence. What happens when an object behaves differently near leverage points built into the architecture of the solar system? Planetary defense frameworks are built on predictability. They assume that bodies respond passively to gravitational forces. ThreeI Atlast did not violate that assumption outright. It tested its margins. The object was not threatening. It was not targeting. It was not accelerating toward Earth. Those claims never appeared in the data. What appeared instead was something quieter and more difficult to process. A body that refused to settle neatly into existing categories. One that combined rarity with persistence. As observational windows narrowed, scientists recognized a familiar pattern from past anomalies. The most informative phases often coincide with the poorest visibility. Geometry, glare, and distance conspire to limit measurement precisely when stress peaks. ThreeI Atlast would pass through such a phase near perihelion. During that interval, direct observation would be constrained. Models would be forced to carry interpretation forward without confirmation. Absence of data is not evidence, but absence under pressure is consequential. When the object later re-emerged, it did so without obvious disruption. Its motion remained coherent. Its orientation appeared preserved. Whatever forces acted during reduced visibility did not destabilize it. Continuity after stress sharpened earlier questions. If nothing happened, why did uncertainty remain? If something happened, why were its effects so subtle? By this point, the narrative around ThreeI Atlast had shifted irreversibly. It was no longer framed as a curiosity. It became a case study in how anomalies accumulate without declaring themselves. No single observation demanded alarm. No single model collapsed. Yet the system as a whole felt increasingly compressed. Acceleration that did not fade. Structure that did not unravel. Geometry that did not randomize. These were not proofs. They were pressures. As calculations continued and the object moved steadily onward, one conclusion remained safe and unavoidable. ThreeI Atlast was not behaving in a way that invited easy closure. And as long as that remained true, every projection forward carried more than mathematics. It carried the weight of unresolved behavior moving, steadily and silently, through regions where small forces matter most.